Okay, this is a TMUA paper, 2018, paper number 1. Let's get straight into it. Bit of integration first. I'm going to deal with this thing on the bottom first. This is x to the power 1 times the square root of x, which can also be written as x to the power of a half. Then you add the things together to get that this should be x to the power 1.5. I'm writing it as a decimal because I'm lazy. Then we can separate, we can divide this by that and then this by that to get this. And this is good because I've put it back into fractions because I'm just so inconsistent apparently. But yeah, I've just divided this by this to get the minus 1.5 power, this by this to get the minus half power. And then I can integrate, right? I can increase that by 1, divide, increase that by 1, divide, put in the limits 4 and 1. When you put in 4 to this, you're doing 1 over 4 the square root of, which is 1 over 2, which times by that just to make a minus 3, and so on. I don't need to explain this, I don't think. Just a nice warm-up question. Question number 2, so the correct answer is, I guess, minus 1. Question number 2, we've got an arithmetic progression, so we go a, then a plus d, then a plus 2d, plus a plus 3d, and so on. It's talking about the sum of them. So this is the formula for the sum. You need to go into the TMUA paper just knowing this. So it's telling us that s of 5, the first 5 terms, is equal to s of 8. And now I know I can put in n is 5 and 8 into these, so that's good. My a, I'm just going to call it a and d. So s of 5 is 5 over 2, because n is 5, and then 5 here, and s of 8 is likewise with the 8. But I can simplify these a lot, because obviously this is a 4, and then I can multiply this out, expanding the brackets. These 2's cancel, the 2 cancel with that 4, just leave a 10. This is just 4, and this is 7. Expand it out, and you get this. But these two things are equal, right, as I've written. So this is equal to that. It wants this in terms of a, it looks like, because that's what the answers are in. So take away 5a from both sides, take away 18d from both sides. When you divide by 3, I think you'll find minus 60. Question number 3. Okay, draw it. These are circles. This is a circle, center minus 2, 3, radius root 18. This is a circle, center 7 minus 6, radius root 2. Put those 2 points down. Now I'm first going to find the distance between the centers. The difference between the centers, well, okay, so I'm looking for that length. Well, the difference in the height is 9, and the difference in the width or x coordinates is also 9. So I could do some Pythagoras here, or I could notice that this is my 1, 1 root 2 triangle, and this is just a bigger version of that, right? This is just a triangle that's 9 times the size of that, so this is going to be 9 root 2. And I saved myself doing Pythagoras. But that's, of course, not the answer, because the answer is the shortest distance. So if I actually put the circles down with root 18 and root 2, the answer is going to be 9 root 2, which is this whole distance. Take away this distance, take away that distance. Now that just makes 8 root 2. That's 9 times 2, which is root 3, which is root 9 times root 2, which is 3 root 2, and then you just get 5 root 2. Nice question. Question number 4. So this is just a simultaneous equation. Let's rearrange this for y, and then let's put that bad boy straight into here. Expand this out. Ends up being a quadratic. I'm looking for when this quadratic has 2 distinct real roots. In other words, when the discriminant is bigger than 0. The discriminant being b squared minus 4ac. So b is this term, a is this term, and c is the minus 4. So b is that. 4 times a, which is 1, times c, which is minus 4. Sort this out. Now the thing is that this is always true. No matter what value, not real value of a you put into this is always true, because when it squares it becomes positive, times by 4 still positive, plus 16 still positive. So this is true for any value of a. Question number 5. Okay, so a bit of a remainder theorem here. I've done this, I think, on every single TMUA paper, so you need to know the remainder theorem. If f of a is equal to k, then x minus a leaves remainder of k when dividing it. So the fact that this has been divided by that and left remainder r means that f of minus 2, because to make this match you'd need a as minus 2, because x minus minus 2 is plus 2. So that means f of minus 2 is equal to r. That's what the remainder says, because it works in both directions as well. I've written it working in if this, then this, but it works in both directions. So therefore, f of minus 3 is s. I've said before in a video, I think there are some textbook questions on remainder theorem somewhere in the Pearson Active Learn section. Find some and just practice it, because it's going to come up. Anyway, I'm going to put minus 2 and minus 3 into this here. So f of minus 2 is that, which simplifies to that. F of minus 3 is that, which simplifies to that. I know this is equal to r, and I know this is equal to s. I'm looking for the largest possible r minus s. Let's do r minus s. That's going to be this. Sort it out, be really careful with the negatives. And now I'm looking to make this as big as possible. So how do I make this as big as possible? Well, I want this here to be as small as possible, because I'm taking it away, and I want that to be as big as possible. It's completely unreliant on c, so I'll just throw c into the middle. But I want a to be small, because that way I'm taking away less. I want b to be big, and then c I'll just put in the middle. So a, well, the only choices I have are 1, 2, and 3 in this question. So I want a to be 1, b to be 3, and c to be 2. And when you do that, you put those in, you get the answer of 17. Question number 6. There's a few ways to do this. I said that tan is sine over cos always. You can replace any value of x that you want here. So I'm going to use 2x, which means tan 2x is this over this. If I divide both sides by cos, it's 2x here. Then this is my definition of tan, and this is just 1 because it's this divided by itself. Now I could run with this, and I could do this graphically, but I thought it was slightly easier to move the x down to here, dividing both sides by x, and do this graphically. What do I mean by graphically? Well, I'm just saying this here is asking, when does the graph y equal tan 2x intersect the graph y equals 1 over x? Because if you were asked this question, you could just set these equal to each other, right? So I'm going to ask, when do these intersect? I'm actually not going to ask that, because I'm not being asked for the answers here. I'm being asked how many there are. So all I'm really asking is, how many times does this happen in this bound? So let's draw it. Here's the graph of tan between 0 and 2 pi. But I'm not looking at the graph of tan, I'm looking at the graph of tan 2x, which means this is squashed inwards, which means it does this whole thing twice, right? So it's going to look more like this. Y equals 1 over x is going to look like that, and I just need to place these on top of each other to make it look like that. And now I'm just counting solutions. I'm counting that this has 1, 2, 3, 4 solutions. So the answer is E. Excellent. Question number 7. Okay, so how do I make an x to the 6 from this expression, this expansion here? Well, I need 3 of those, because that's going to give me the x to the 6. And if I'm taking 3 of those when I expand, then I must be taking 4 of those. Like if you imagine writing this out 7 times, you're going to bounce along 4 ones and then 3 of these terms. So the coefficient here is going to be 7 choose 4, 7 choose 4 ones, 1 to the power 4, which is just 1, and then this to the power 3. And these powers come from the fact that you could be choosing different options for the 4 ones and 3 ds. But I'm sure your teacher has explained this in the past. Now, why, if I'm instead of choosing 4 ones and 3 of those, why is this 7 choose 4 and not 7 choose 3? Well, it turns out those two things are the same, and I'll explain that a little bit later. Exactly the same logic for this one. To make an x to the power 6, I'm going to need to take 6 of those. And if there's 10 options in total, that means I need to take 4 of those bad boys, which means it's 10 choose 4 of those. 10 choose 6 gives you the same thing. I'll explain why in a second. K to the power 4, because I'm taking 4 of them, x to the power 6. Now, how do I work out 7 choose 4 and 10 choose 4 without a calculator? Well, this is the definition of the choose. It's n factorial over n minus k, k factorial. So this one here is going to be 7 factorial. I don't know why that says a 12. That's really annoying. That should totally say a 7. Let's just change it, because otherwise it would annoy me. Spoilers there as well. So 7 factorial is 7 times 6 times 5 times 4 and so on. But notice how a bunch of that cancels with the biggest factorial on the bottom, in this case 4. So all of that just goes away with all of that. And you're left with 7 times 6 times 5 over 3 times 2 times 1. Now this one ends up being nice because 3 times 2 is just 6, which means these two cancel with that. And you're just left with 7 times 5 divided by 1, which is 35. This just makes k cubed x to the 6. That's just a 1. And likewise for 10 to the power 4. Now the reason 7 choose 3 is the same is because when you put 7 choose 3 in here, this one here becomes 7 minus 3, which is 4, and this one becomes a 3, and you just end up with the same things on the bottom. And likewise over here, this is the same as 10 choose 6. But anyway, if you do 10 choose 4, eventually you figure out that it's this, just doing the same method. And therefore the coefficients, which is 210k4 equal 35k3. I know k isn't 0 because it says so, which means I can divide by k cubed, and then I divide by 210. I hope this is there, but it's not, so I'm going to have to actually simplify this. Divide both by 5, I guess, and then I notice that's easy, that's a 6. Good, question number 8. Geometric regression this time, we did arithmetic earlier. So the sum of a geometric is 6. So a geometric regression is just a, and then you multiply that by r to get ar, then you multiply that by r to get ar squared, and then so on. And now the sum of a geometric regression, if r is between 0 and 1, is this, where a is the starting term and r is that thing you're multiplying by. And it's saying that the sum of this is 6. So that means that this expression here, a over 1 minus r, is 6. Now, when you sum the cubes, now the cubes of these are a squared r squared, a squared r4, when you square that, remember, out to the 4, and a squared r to the 6. Now, the starting term here is a squared, and the common ratio that you multiply by is r2, right? R squared. So that means and because that all adds up to 12 apparently, that means that this equals 12. Now it's asking me to find the sum of the cubes. I don't feel like I'm going to be able to do that unless I find a and r, because these are actual numbers. It's not in terms of a and r, it's just asking me for a and r. It's asking me for a number, so I think I need a and r. But this looks a bit like a simultaneous equation, so I think I can do it. There might be easier ways to do this, but I think at this point, I've done so much of this. When I see this, I just hone in on this bad boy. It's 1 minus r times 1 plus r. It's a difference of two squares. So that's what I immediately did. And then I noticed, well, this looks a bit like this. A squared is a times a, and then I can break this fraction apart to be this. Right, so I did this, then this, then this, then this. But I can just break that fraction apart like this, right? Because if you were to do this, you'd get to this, which is this, I guess. But this bit here is just 6 from there. And divide both sides by 6, and you get that this thing here is 2. And this looks like an easier simultaneous equation for me to work with. So I'm going to work with this simultaneous equation instead. If I times both sides by 1 plus r, and then sub it into this guy here, I get this times both sides by 1 minus r. It just ends up being a lovely linear equation in r, which I can solve very easily. And then, of course, I put in r as a half into here. Or actually, into here is easier, isn't it? Much easier. And you get a is 3 and r is a half. So I found a and r. Which means, well, this is the original sequence. This is the squares. What do the cubes look like? Well, it's a cubed r cubed, a cubed r6, and then a cubed r. Those are the cubes. And I'm looking to sum this up. So it starts with a cube, and it has a common ratio of r. It starts with a cubed, common ratio of r cubed. So putting that into this formula, but I get, this is the formula, but I know what a is. That's 3. So a cubed is 27. I've written this confusingly, haven't I? I should have put a cubed r cubed here. Yeah, apologies for that. Hopefully you can follow this anyway. I'm just saying that the first time is 27, the ratio is 1 over 8. So those are the numbers that go into here. And then I sort this out. The 8 can bounce up to here. I hope that that's 216 because that's the only one that's dividing by 7, and it is. And I get my answer. Yeah, nice question. Question number 9. Find the set of values that has 3 distinct root roots. Now, this is a cubic. It's a positive cubic, which means it starts down here, ends up here. So it's very step-like, this question. Very step-like indeed. Goes through the y-intercept of c. Now, I'm just going to pretend c is positive. It might not be, but it's not going to make a difference in the end, and I'll explain why later. Now, for this to have 3 roots, it's got to have a turning point up here and a turning point down here. The turning point one of them needs to be above the axis and one needs to be below, because that way it passes through the axis again as it gets to its other one. If this turning point was up here somewhere, then it would only have this one root just there, right? So one turning point needs to be above, one turning point needs to be below. So what I'm going to do is I'm going to look at the stationary points of this, or the turning points, and evaluate that. So if this is f of x here, if I differentiate it, I get this. If I set that to be 0, because stationary points are at 0, I get this, divide everything by 6. This factorizes very nicely, and I find my stationary points are at 2 and minus 1. So this graph looks a bit out. My stationary points are at minus 1 and 2. Now, I know they're stationary. These aren't roots, so I can't put the x here. These are stationary points, so they might be somewhere along, anywhere up here or down here or anywhere. So I'm going to find where it is. So if I put in 2 into f, I find exactly where it is on the graph now. So I'm going to put 2 into this, which gives me c minus 20. So when x is 2, y is c minus 20, which I'm just going to pretend is down here. I tend to put a line through my stationary points to remind me that when I draw this, it goes flat through there. Now I'm just going to pretend c minus 20 is down here, and I'll explain what I'm doing later. Now I'm going to find where the graph is at minus 1. So f of minus 1, do this a bit quicker, is c plus 7 apparently, if you just put that in. Now I know c plus 7 is above c, so that could be up here somewhere. Again, flat, and that's the point. So my curve currently looks a bit like this going through here and has 3 roots, right? Now, I think, did I draw the curve in? I did not at any point. That's annoying. But we can just imagine the curve. The curve looks like this through here, through here, through here, with the 3 roots I was talking about earlier. Now, for this to happen, though, I need 2 things. I need this thing here. I need it to be above 0. I need it to be a positive thing. So I need c plus 7 to be positive, which means I need c is bigger than minus 7. And this is why it didn't matter really where I put the c, because it doesn't really, if you change this c, you just move the entire graph up and down. But that's not relevant. It's only the stationary points that are relevant, as I've explained. And I also need this here to be less than 0. So I need c minus 20 to be underneath the line, because I need 1 over and 1 under, which of course gives you c is less than 20. Which of these refers to c greater than minus 7, less than 20? Well, it's that one there. And we get our answer. And the graph looks a bit like this, which I should have drawn in, I think. But anyway, question number 10. Okay, so the first time I've seen moduluses in TMUA, so that's kind of interesting. Greatest possible value of this. Now, I notice when I multiply these 2 numbers together and take the mod, taking the mod just makes it positive. So it doesn't matter whether x and y are negative. All I want to make this as big as possible is I want x and y, I want the moduluses of x and y, I guess, to be as big as possible. It could be minus 100 and minus 200, but they would multiply to make it, well, they multiply to make a big number anyway. It could be minus 100 and positive 100. But when you take the mod of those 2 things multiplying together, you get a nice big value. So I just want the values of x and y to be as big as possible. So I look at these 2 expressions here and I go, well, how do I make x work here? Well, you could choose x is minus 4, because 2 minus minus 4 puts you on the edge of working. So that's okay. But also, you could choose x is 8. 2 minus 8 is minus 6, but modded is 6. So that's also on the edge of working. But this is the bigger one, so I'm going to choose it. And likewise here, I could choose 2. 2 plus 2 is less than or equal to 4. Or I could go the other way and choose minus 6. Minus 6 plus 2 is minus 4, which modded is 4, which is less than or equal to 4. And this is the bigger one. The size of this is bigger. So I'm going to choose 8 and minus 6, which multiplied together to make 48. But when you mod them, they make plus 48, which is the biggest one I can make. And so it's 48. Quite a nice question. Not seen much like it in TMUA before. Question number 11. Okay, so it's talking about normals, so my first instinct is to find the derivative. So the derivative of this is that, and this is at the point PQ. So if I put in the x-coordinate P, I get the gradient of this curve at this point is minus 2p, which means the gradient of the normal, which is this line, the gradient of the normal, which is m, because m is the gradient of this line here, is 1 over 2p, so positive and flip it over. So I know m is 1 over 2p, but I know the line goes through PQ. So I can put that in here. And the p's cancel really nicely to give you just a half here, and a half plus 5 is 5.5, and that's what q is. So I know what q is, but it's asking me for p. So what I'm going to do is I'm going to go back into this one, because I notice if I put in my known q into here, this graph here, it goes through p 5.5, or pq, but I know what q is now. So I can just put this in, and I can solve this for p. Now, when I square root this, I'm going to get 3 over root 2, which isn't an answer, but I can rationalize to get this. But also, when I square this, I might be looking at a plus or minus, right? Now I'm not, because it's told me that the gradient of the line is bigger than 0, which means this is bigger than 0, which means this is bigger than 0. So I'm only looking for the positive answer. Not that it matters too much. Oh no, it does matter, doesn't it? Because both options are there. So I know it's the positive, because I know m is positive, which means this is positive, which means p is positive. Which means I'm choosing the positive one here. Cool. Number 12. Okay, so this is a quartic equation. Now, if it's factorized like this, what that means is the roots are at 0, p, q, and r. So that's nice. Those are all the roots. It's given me where it goes to the axis. That's really nice. Now, also notice, tricky here, this one is written the other way around, which means if I were to expand all this out, I would end up with a minus x to the 4 term. Which means this is a negative cubic, which means it starts down here, sorry, negative quartic, which means it starts down here and ends down there. So this graph has to go through all these points and then there, so it looks a bit like this maybe. Bit of a random drawing that, but it looks a bit like that. Best I could do in PowerPoint. Now I know that the integral between 0 and r is 0, which means if I label these areas A, B, and C, I know when you've got an area above the axis, that's a positive number, and below is negative. So for these things to add up to make 0, I know a plus b plus c is 0. Now, if I only integrate between 0 and q, which is just from here to here, I get minus 2, which means a plus b is minus 2. But I can easily see now that if I just do this, take away this, I get c as 2. So that's fine. If I integrate between p and r, which is just between these two bits, I get b plus c is minus 3. But I know c is 2, which gives me b is minus 5. And then looking back up here, a plus b plus c is 0. That gives me a is 3. What's the total area? Well, the magnitude of this area is 3. The magnitude of that area is 5, and that's 2, which means they all add up to make 10. Question number 13. Oh, let's get this one done in 30 seconds. So I won't really, because I'll have to explain what I'm doing. This is a gradient function. So we've got to think this function here is describing the gradient of some other function, because that's what f dashed is. So if we're picturing that function on our heads, this is a positive gradient right now. Now, I'm pointing at it and you're shouting at me, no, that's a negative gradient, sir. Look, it goes from top left to bottom right. No. The value of this graph, which is the gradient itself, the value of this graph is positive over here. So the gradient of the graph it's describing, is a positive gradient, right? So because, if you pick this value, say this is minus 5, the value of this graph is a positive number, say 10. The gradient of the graph that you're describing is 10. It's a positive thing, right? Now here, the gradient is 0, because when you're on here, the function is 0, right? Y is 0, f of x is 0. So here, the gradient is 0. So the gradient of the line we're trying to talk about is 0. It's flat. It's flat there, just for a moment. I've drawn it really long, but I'm just trying to represent what I'm talking about. But the gradient is 0 here. Now the gradient is negative, so our line starts going down, or our curve that's made up of my lines starts going down, because its gradient is in the negative numbers. Now here, it's still in the negative numbers, but it's sort of getting less in the negative numbers. So it starts going down by a shallower amount, until here, where the gradient is 0, momentarily. And now the gradient starts going back up again, because the gradient is positive here. It's in the positive numbers. So our graph starts going back up. It starts going back up slower and slower, and slower, and slower and slower. Now, think about this. This is still a positive gradient, but it's getting less positive, because it's going back down to 0. So our graph is it's still a positive gradient, but it's less positive, right? It's like it's curving less and less positive until here where the gradient is 0 momentarily, and then it starts going back up again. So the gradient is positive, so our graph starts going back up. So this actually ends up being a point of inflection. Now, where is the minimum? It's there. That's our minimum, because our graph sort of does this. Then inflection, then up. So that's the minimum C. I love those questions. I think it's really cool to think about that kind of thing. I don't know whether I'm just weird. Question number 14, moving on as fast as possible. Just put these 2 points into this equation, like so. Just be careful that the logs are on different sides. Now, this seems like the easier one to deal with, because when you take away 4 from both sides, you just get this. Now, this is a product. It's this times this is 0. So either m is 0, or log to base 2 of p is 0. Now, this is fine. This does work if p is 1, because 2 to the power 0 is 1. So, okay, that's one solution, right? m0, p1. It's one of these two things is my answer. Now, if m is 0, what happens here? Sorry, I've said that wrong, haven't I? M is 0 and p is 1 don't happen at the same time. P is 1 is a solution. If m is 0, p can be whatever the hell you want, right? P is 1 is a solution if m isn't 0. M could be anything else. Yeah, I've said that wrong, didn't I? But either m is 0, in which case p can be whatever you want, or p is 1, in which case m can be whatever you want. Now, if m can be whatever we want, in this case, that doesn't really help us, but we have the p as 1, so that's fine. If m is 0, I can just put that into here, and I'm looking for that. And now I'm looking for 2 to the power 4 is something, that's 16. And so the solutions for p are 1 and 16. Okay, question number 15, just a quadratic substitution that we're going to have to make here. Let's sort this out a little bit first. I'm going to halve these two numbers here, because that's what you do when you multiply out brackets. Then I'm going to say, well, this here, when you add indices, that's the same as multiplying numbers of the same base. So this is 3 to the 0.5x times 3 to the 2. and 3 to the 2 is 9, so that's just 9 lots of that. Don't know whether I should have put in an extra stage of working there. Just pause the video and break up. This is 3 to the power of that times 3 to the power 2, because you add the indices when you're multiplying numbers with the same base, and then the 3 squared is that. Now I'm going to make a weird distribution. I'm going to let y squared be 3 to the x. So this is y squared. And now I'm going to raise both sides of this to the power of a half. Because that will, if I raise this to the power of a half, it just makes a y. And if I raise this to the power of a half, it makes a 3 to the power 0.5x. Because you multiply that out for 3 to the power 0.5x, which gives me this, which is nice. That should be a y squared. That's annoying. Yeah, apologies. So this bit's fine. The substitution y works in here, and then it's just 9y. This should say y squared, because I'm replacing that with a y squared, so that should be a squared. Anyway, then this factorizes, so either y is this or that, so either 3 to the power x to the power 0.5 is that, and now I can do the reverse of what I did before. I can raise both sides to the power 2 to cancel out the 0.5s. Essentially, square both sides. And of course, now my solutions are x is log base 3 of 25 or log base 3 of 16. Now it wants the sum of the solutions, so I'm going to have to add those two things together. And you could multiply 25 and 16 here, because that's what happens when you add logs. Or you could notice this is a square number, and so is this. I know that because I had to do it to get them. Which means I can move the 2 to the front in each of them, then I can factorize the 2 out, then I can just multiply the 5 and the 4 for 20, and I get my answer here. Okay, cool. 5 to go, I think. Find the value of b that minimizes the distance. So we've got some quadratic, and we want to minimize the distance between the origin and the stationary point. So the stationary point of this quadratic, I can just complete the square to find, right? So halve this number, take away the square of what I just did, what I just found when I halved. And the stationary point of this is at minus b over 2, and then I've swapped the order here just because. So what this graph looks like is, now b is positive, which means minus b over 2 is indeed over here. It's just a quadratic, and this turning point is at minus b over 2, 2 minus b squared over 4. Now, I don't know whether this is positive or not, but I also don't care. I'm just looking to minimize this distance here across. Now, I can just do some Pythagoras to do that, right? Because I know the distance flat across is b over 2, and up is, or down, it doesn't matter which way, is this. So I've got that this diagonal distance that I'm trying to minimize, that squared is equal to that squared plus that squared, just from Pythagoras. You can sort this out, I'm sure. Make sure you expand this out properly, and get it done in the correct way. Add them together, and I think you get this. Now, I'm looking to minimize the distance. So I'm looking to minimize this thing here. So my new question is, minimize this bad boy. Now, you could maybe do some differentiation if you wanted here, but actually the easiest thing to do is to spot that this is actually a quadratic in disguise. It's a new quadratic in disguise. And to find the minimum point of a quadratic, you can just complete the square again, because that's probably the easiest way to find the minimum point of quadratics. So I can complete the square on this. I'm first going to take out a power of 1 over 16, or a factor of 1 over 16, just because completing the square on this is a bit easier. And then if I halve this number from minus 6, keep this as a b squared, and then put a bracket squared there. Notice how when this expands, it just makes b to the 4 minus 12b squared, which is there, and then the plus 36 is cancelled out by this that I've introduced, which is what completing the square, I guess, does. And now, of course, this tidies to this, but I know what the minimum point is, because this is always positive. I know the minimum, the lowest I can make this is when this bit is equal to 0. That's why completing the square works, right? This is always positive, so the smallest I can make it is, well, it's always positive or 0, so the smallest I can make it is 0. So the smallest I can make this is when this is 0, which means b is plus or minus root 6, but it's positive, so it's root 6. Lovely question. I've said that a lot this paper, haven't I? I did enjoy this paper. Okay, I enjoyed this question as well. Question number 17, so it's about means and stuff. Let's just quickly show you a nice GCSE question first. The mean height of this is this, and so on. When you get questions like this, pause the video and just do it really quickly yourself. But I think what you'll have been taught is you talk about totals a lot. Like if there are 6 children having a mean height of 165, essentially you just pretend that they're all 165 centimeters tall. And then you say, well, I've got 6 of these clone children, which means I have a total height of 6 times this of 990 centimeters. Now I take out this child who actually only has a height of 155, which means my total height goes down from 990 minus 145 to 835, and that's the total height of the remaining 5 children. So then I divide that by 5 to find my average height of the remaining 5. So that's nice and simple. Then you step it up, right? When you take a kangaroo gray paper, and they talk about the same kind of thing, but they don't give you a number of students, right? Here they gave me the number of children I was looking at, but here they haven't given you any numbers. So what you do, or the easiest way to do this, is just to make up a number. Make up that 100 students took this paper, and then work out that if 100 students took the paper with a mean score of 6, then they got 600 total marks between them. 60% of the students passed, so that's 60 students. And the mean score for them was 8, which means 60 times 8 is 480. That's the total marks the passing group got, which means the non-passers, of which there are 40, got 600 minus 420, so 120 marks. And then you just do 120 divided by 40 to find that their average is 3. Now, we have a problem with my group, with my question, which is they haven't given me, just like Kangaroo Gray, they haven't given me the number of pieces of data in the first set or the second set. And this is a problem because while I'm completely okay to make up one number, if I'm ever doing a question like this, I'm completely okay to make one number up and run with it, I'm not allowed to make up 2. I can't make a number up for this first set and then a different number up for the second set. And I can't just make up the same number twice. Things start not working, and you'll kind of see why in a second. So I am going to have to do a little bit of maths first. So I'm going to set up a table. Set A has a mean of 15. Set B has a mean of 20. So the pieces of data in set A, I'm just going to call N, and I'm just going to call this piece of data in set B M. So I'm just saying there are N pieces in here and M pieces in here. And now the total value of all the data in this set is just 15 times N. Right? Imagine there were 10 pieces of data with a mean of 15. That would mean that there was 150 in total, right? Because you just pretend they're all 15. Got 10 of them, so it's 150 in total. You multiply these together, just like I did in the first examples. And likewise, the total here is 20M. Now, something happens here. You exchange one piece of data from the first set with the second set. So you take a piece of data out from here, and you put it in here, and out from here, and put it in here. Now, this changes the mean, apparently, from 15 to 16 and 20 to 17. However, what does it not change? Well, it doesn't change the number of pieces of data in each set, because you've taken one out of here, but you put one in from here, right? So you just did a swap, right? So there's still this number, which means the total I can still describe as 16N and 17M. Now, what else hasn't changed? Well, if you've just swapped a piece of data from one set to the other, the total of all the pieces of data added together has not changed because you haven't changed any individual data. You've just swapped it from one set to the other. So the total, the 15N plus 20M, the total of this set plus the total of this set, must equal the same thing at the start before you did the swap as the end. So this total here must equal this total down here, right? Because none of the data's changed value. You just swapped it from one place to another. And I can sort this out, right? I can take away 15N from both sides, take away 17M from both sides, and I end up with this beautiful expression. Why is this so beautiful? Well, because what this tells me is that however many pieces of data are in sets B, if I multiply it by 3, I get the number of pieces of data in set A. And why is that so helpful? Well, think about the second example I showed you where I can make up one number, right? I'm allowed to make up one number. So what I'm going to do is I'm going to make up this number as 30. And then I don't have to make up this number anymore because I just know that it's a third of this one. So I've only made up one number, which means I'm fine. The total is just 15 times 30, which is this. The total of this set is 20 times 10, which is this. And now the mean of the set by combining everything, well, you combine the number of pieces of data, which gives me 40. And 40 is just a made up number. Like I'm making this up, but it's okay. I'm allowed to make up one number. And the total of all the pieces of data is the total of this plus the total of that. So it's going to be all the data summed up, which is this plus that, divided by the total number of pieces of data. And you get this, which you can eventually figure out is A. So yeah, a really nice question, quite tough. Question 18. Okay, so if we draw the sine graph, this is saying there's a line x equals a. Now x equals some number is a vertical line, like this or this or this. And it's saying that the graph is symmetrical. Now, for sine to be symmetrical around a vertical line, the vertical line must go through the top points or the bottom points. That was such a terrible description. Must go through, I completely mind blanked what you'd even call this, the turning points of sine. It must go through either the turning point up here or the turning point down here. It's not symmetrical here, for instance, right? Like it's only symmetrical around the turning points, whether they're down here or up here. Okay, so what I'm going to say is I want sine 2x, and this is the even if you do some transformations. Now, I could do this question via doing these transformations, but I'm not going to because you get into a mess, which I might explain in another video. But what I'm going to do is say, well, if this is symmetrical about some vertical line, then the sine graph must either equal 1 or minus 1, right? The only place this graph is symmetrical is about when it equals 1 or when it equals minus 1. So I want either this to be 1 or minus 1, and I can deal with this separately. I can deal with them separately like this. Now I'm going to take sine inverse of 1, which, remember, sine inverse of 1 gives me lots of different values, right? It gives me pi over 2, or it gives me 5 pi over 2, or going backwards, it gives me minus 3 pi over 2. Give me lots of different values. I have to put down a few of them. So I'm going to put down the first negative, the first one you would normally think of, and then the next one as well. And then I'm just going to sort this out. I'm going to change all these denominators to be over 6, and then add in 8 pi over 6 to both sides, and you get this. Now, it wants me to have a positive value of 8. That line that it wants me to put down needs to be a positive value. So what I'm saying here is that this graph is symmetrical about the line y equals minus pi over 12, but that's not positive. This is the smallest positive. So that's my answer so far, but I still need to deal with this case because I could also be symmetrical about the bottom parts of the graph, couldn't I? So I need to deal with that as well. Do sine inverse of minus 1, and you get these options. Notice how it's always an odd number on top, and then it just swaps between. So sine of 1 is minus 3, 1, 5, 9, 13, and sine minus 1 is minus 1, 3, 7. Like it's just, it includes them all. It's just swapping from this to this. Then I can make all the denominators 6 again, then add 8 over 6 pi, and I get this. And actually, that's the smallest positive one. Once I divide by 2, I guess, that's the smallest positive one. And so the answer is B. If you try and do that using graph transformations, you get into a mess that I'll try and describe in another video at some point, somewhere. And I'll link it if I ever do make that video. Question number 19. This, I guess, is there randomly. Anyway, triangle ABC. Let's draw it. AB is 10, BC is 7, angle A is theta. And right, so theta is a certain specified angle. So when I first read this of the two possible triangles that could be drawn, I thought this was talking about, oh, you could have one triangle that's like this, and then another with a different theta. But theta is locked. It's a certain specified angle. So how else do you draw this triangle? By locking theta, locking 10 and locking 7, where you draw it a bit like this, where you move the 7 up to here instead. So, okay, that's cool. Now, we've got two different side lengths we can have over here. We've got the x or we've got the y. Now, the other clue I've been given about this question is that the larger triangle has 3 times the area of the smaller one. So this is the area of a triangle. So that means half times 10 times x times sine theta is the area of this, and half times 10 times y times sine theta is the area of this. But this is a third of that. Or this is 3 times that. And it's fairly obvious when you think about it, but that means that y is just a third of x, or x is 3 times y. Because everything else is identical, right? Half 10 sine theta, those are all the same. So that just means that if I call this y, this is 3y. Okay? Now I'm going to do some cosine rule because it's talking about cos. So let's do some cosine rule. 7 squared is 10 squared plus 3y squared, which is, I've done that in one go, I guess. Maybe I should have put the working down, but it's 3y squared is 9y squared. 3y in brackets squared is 9y squared. You know what I'm talking about. You simplify this and you get that. Do the same cosine rule over here, simplify it and you get that. Now, this is confusing, but if you really squint, this is essentially just a simultaneous equation because there's 2 unknowns, y and theta. So it's just a simultaneous equation. Now, what do you do when you have simultaneous equations? Well, one thing you can do is stack them on top and take away, which is what I've done there. And the reason I noticed that is because the 51s will go away, which seems positive. Now, I know y isn't 0 because y is a side length, remember? So if it was 0, the triangle wouldn't exist. So I can get rid of a y, and then I can rearrange that for this. And once I have that, that's excellent because I can put that in to one of the equations, and then I'll only have an equation in theta, which is exactly what I want. So I'm going to put this y into this equation here, do all the stuff, and we're pretty much there now. I actually got stuck here for a long time because I was trying to root 51 and root 75. I was like, well, none of it's here. And then I realized that you can simplify this fraction by dividing both by 3, and then you can square root, and you get this answer here. Now, when you square root, why can't you have a negative value here? Now, you can't because none of these are negative, so you can just tick the right one and move on. But maybe just to describe exactly why you can't have a negative, look back at the picture I drew. Theta is opposite the 7, which is not the biggest side in the triangle, which means theta can't be the biggest angle in the triangle. Depending on the value of y, one of these two angles must be the biggest. Now, if theta isn't the biggest in the triangle, it can't be bigger than 90. It has to be something less than 90 for it to be not the biggest angle in the triangle, which means that cos theta can only be between theta can only be between 0 and 90, which means, and cos theta is always positive between 0 and 90. So that's how I know this is a positive value, because this is definitely not bigger than 90, because it's not the biggest angle in the triangle. Anyway, question number 20. Lovely question, this. We're going to need to use this fact. How do we know this? Well, you go all the way back and you learn the definition of sine and cos. If you have what's called the unit right-angled triangle, hypotenuse 1, right angle here, angle x, this side is defined to be cos theta, and this side is defined to be sine theta. That's the definition of sine and cos, or at least one of them, and probably the most useful for GCSE and A-level maths if you want to try and understand the stuff. Now, how do I prove this from here? Well, if this is a right angle, which I'm telling you it is, then this angle must be 90 minus x, right? Because 180 minus 90 minus x is 90 minus x. Now, turn your head to the side, because if sine of x is defined to be the length of the opposite side of x in a right angle triangle hypotenuse 1, then when you turn your head to the side, this here is the opposite side of this angle 90 minus x in this right angle triangle hypotenuse 1. So this side must be sine 90 minus x, and this side must be cos 90 minus x for the same reason. It's the adjacent side to this angle, and so this equals that because they're describing the same side, and so this is true. Now that I have that's true, I'm going to start converting a lot of these. So I'm going to square both sides of this first. I mean, that's sure, I can do that. And now I'm going to say, well, okay, this is true for x is 0, which means this is true. But it's also true for x is 1, which means this is true. And it's true for x is 2, which means this is true, and so on. And what I'm going to do is I'm going to replace the first half of this list with coses. I'm going to replace sine squared of 0 with cos squared of 90, sine squared of 1 with cos squared of 89, sine squared of 2 with cos squared of 88, and so on. I'm going to do that all the way until the halfway point of 45. After the halfway point, I'm going to keep the signs. And I'm going to keep them all the way to the end. Now, why am I doing this? Well, because of this identity here, this gorgeous identity here, which says that for any value of x that you put in, cos squared plus sine squared of that value is equal to 1. So if you put in 88, then these two things add up to 1. And so matching the pairs up, you can add in any order you want, right? Which means this one plus this one, if I add those two together first, they give me 1. This one plus this one, they give me 1. This one plus this one, they give me 1. And these two give me 1 as well. That should be these two give me 1 as well. So everything just gives me a bunch of 1s. All of them pair up. Now, how many pairs are there? Well, it goes from 46 all the way to 90, so there are 45 pairs of 1s. And now, what's the only one that doesn't pair? Well, there it is. So I just need to figure out what this is. Well, cos of 45 is 1 over root 2, which means when I square it, I get a half. And then my answer is 45.5. And that's how we do that.